Yes, sir.
Yes, sir.
Okay, is everybody? Okay, good. See, the last time we talked about the signal. Let's say you have equation, you have a curve, and then you are trying to find the area under the curve. But traditionally, our integral, you can integrate traditional way. I just call this a traditional way. Traditional way, what do? You find the upper limit, lower limit, and then you integrate. Yes? Then you integrate, right? This is what you do. Okay, guys?
Yes, sir.
So
Yes, sir.
when you do, okay, what this equation is doing, this equation is just finding the area under the curve. This is finding the area. Finding the area under the curve. Okay, so now just assume if your fx is well defined, let's say if you know your fx, let's say if fx is cosine, let's say for example, if fx is cosine x or fx is x squared. So all these are, with a lot more functions, you can easily integrate, right? But what happens if you have a function and if the equation, if the integration, let's say an equation, but it's very difficult to integrate using the ordinary method, the traditional method. So in that case, we will use numerical integration. In numerical integration, what we'll do, for example, this is the curve. I'm trying to find the area under the curve. And then let's say this equation is very complicated. So what I'm going to do, I'm going to like split the area under the curve into few pieces. We split the curve into few pieces, like, and then you also put 2 pieces here. So then you have a different area. You have an area of a rectangle is easy to find, right? You can find the area of the rectangle, and then you can add them up together. Let's say area A, area B, area C. The total area is area A, area B plus area C plus area C. So you can simply add them. But when you do this, there's a problem here. You are not going to get an accurate result because you have error. You see, there's an error here. There's going to be error here also. But there will also some error here. So it's not going to give you an accurate result. How would you make this more accurate? Let's say we call this from here to here. Let's say the thickness of this is delta x. If these are equal width, and you call them delta x, the way you can make them accurate is somebody, please, if your mic is on and if you're not using it, please turn it off because I can hear something coming out. If you're a family member, if you don't have a quiet place, I don't know what to do. You have to just mute the mic. But keep interacting with me. If you see any mistake, please let me know. For good approximation, of delta x. What is the delta x? Is the delta x is the width of each of the interval here, right? That's delta x. So it's already mentioned. So the delta x. For good approximation, delta x must be small. So let's say if I want to find to get a good approximation of the area under the curve, what you need, you must make the interval you want to make the interval as small as possible. That is, you want to make a delta x, you want to make the interval of the subsections. You create subsections here, right? Subsections. You create subsection, you want the interval of the subsections to be as small as possible. Delta x must be infinitesimally small. Infinitesimally small. That is, it's like just like saying delta x goes to approximately 0. So, like to be very small, like going to 0 approximately. In this case, delta x will become, when delta x is infinitesimally small, delta x becomes delta dx. So we call this dx when the interval becomes infinitesimally small. Okay, that's the idea behind. All right, any question?
No, sir.
Okay, you guys no question. Because I have no question, then we move to the techniques, some of the numerical integration techniques. The first one we will look at is trapezoidal Trapezoidal Zul. Okay, the first one maybe we will look at is Simpson's rule. Simpson. It's not the cartoon character Simpson. This is maybe some other guy. Simpson's rule is very simple. Simpson has simplified a formula to do that. If there's anything, if, that I'm doing not correct, or if you want me to write bigger or project bigger, please give me some recommendations, suggestions. Because I'm a newbie, I'm still learning how to do these things. So if you are the audience, if you give me feedback, I can improve it. Definitely your feedback will give you extra credit. JJ always give me extra credit, feedback. Yes, earn a bag full of them, extra credit. So you have a curve here. And then you want to find the area. Assume this is the original curve. This is the original curve. And then you want to find a fit. This red line here, quadratic fit. Okay, maybe I will throw away the previous one. That might be confusing you. Okay, that's okay. Just assume for now this is just a quadratic fit. This is the original curve. This is the original curve. Original curve. And then we are trying to find the area under this curve. And let's assume that this curve is maybe complicated or difficult to find the equation for some reason, or some reason it's difficult to integrate this equation. So what we're going to do, we're going to find a quadratic fit to the original curve. Quadratic fit to the original curve. How are we going to do that? Using Simpson's rule. You draw a line from the one end let's say if you call this, okay, we draw a line from here, one. We're going to split this curve into two equal intervals. Maybe not quite two, but you know, just assume they're equal intervals. The length from year to year is h. And then the length from year to year is also h. Let's say these are the 3 points, A, B, C. And then there's the length YL, the length, the height YL that corresponds to this point here, point A, YL. Okay, YL is the height of the curve at point A. Similarly, YB, so YC corresponds to point B, and YR corresponds to point C. Are we all still connected? Let me check the WhatsApp.
Yes, sir.
Yes,
Any
sir.
message or not?
Yes, sir.
Okay, good. Once in a while, make some noise so that I know you guys will be around. Cough or not loud cough, just area under the curve. Once in a while, just throw a question. This is like everything is the area under the curve. Okay, this whole thing, maybe sorry that, you know, it may be looking quite ugly. So the painted one is the area under the curve. So according to Simpson's rule, you can approximate the area. You can approximate the area using this formula. This formula is called A1-41. And it's approximately h over 3 YL plus 4YC plus YR. So this is the formula. You don't ask me how they came up with that. Maybe he was experimenting, and this formula can be used to find the area under the curve. So area is approximately, that's the formula. Let's do an example now. You have given an equation. Okay, call this, just assume that's a curve for that equation. In the lower limit is 1, the upper limit, this is not really an interval. This curve is defined from 1 to 2 when x equals to, for example, this is the x-axis. To be able to find this area, so you have two areas here. There's one area here, tiny. There's one area here. There's a negative area and positive area. There's one little area here, and there's another area here. So we can find this area using Simpson's rule. Area under the curve, we call it lower limit, upper limit, fx dx is equals to what? Ordinarily, you know how to integrate this, right? Now we want to use the A1-4-1 approximation using (1-4-1) approximation. This is a formula: h/3 multiplied by yl 4yc plus yr. You know why the what are those yl, yc, and yr? One is the yl is correspond to the endpoint, yc correspond to the center point. YL really, the left here stands for left point, left. So right is center. Any question? Somebody is calling, but I'm not going to answer the call. You guys have any question?
No, sir.
No, sir.
Sir. No, sir.
Okay. So to solve it, okay, in order to use that formula, we need to split the interval into 2. When you split them, make sure they are in equal interval. Split into two equal subintervals. Two equal subintervals. Okay, let's see. The endpoint is 1. Left endpoint is 1. Right endpoint is 2. So what is in the middle? The middle going to be?
1.5.
1.5.
Okay, good.
5.
1.5. Now another thing you have to note, the interval size is, which is called age. In this case, what is the interval size? What is the length of this interval from here to here? We put this in a different color. Interval size. Okay, interval size. The length, they all equal interval from here to here. Interval size is 0.5, right? Which is called age. Similarly, the interval length from here to here is also same, age, 0.5. So interval size is 0.5. So you have this information, you have the end point, middle point, and right end point, left end point, and midpoint, and then you know the interval size, you can solve this problem. Y left is equals to F1. Y center is F1.5. Y right is F2. Agree?
Agree, sir.
Agree. And G, you came late, right?
Wi-Fi connection got corrupted, sir. That's why.
Okay, if you guys are truly having problem, my sympathy to you. But later you can make sure you watch in the video and get back to me if there are any questions.
Okay, sir.
So therefore 1 to 2 fx is, you go back to this formula, is h over 3. Maybe I can just take this. I'm just bringing it over here for reference so that you don't get confused. Now the rest is plug and chug. Okay. Y is F1. YL is F1. If we go back to this equation, Fx is this is Fx. Let me put here. So when you put 3 log 1, so this is going to be show in detail how to evaluate this ln 1 minus 1. This will be 3 ln next one is 3 natural log 2 minus 1. So you have to evaluate all these things. And these are the guys who we call YL, YC, and YR. And then you put them in this formula. So let's do that. So that's going to be equals to, what was our age? Age is 1/2, right? Over 3. You know, if you have the calculator, you can calculate this. If you don't have the calculator, you can just leave them inside here. So you go ahead and evaluate this. You will get roughly around 1.57503865. For numerical analysis, you should give as many decimal places as possible, depending on the how small the number result is. For a small number, you must give more decimal places. For a larger number, you can get away with the smaller decimal places. It all depends on the problem you're working on. Okay, is this, for example, clear?
Okay,
Yes, sir.
Okay, I have just one more example.
Yes,
After
sir.
this, we will hit the road. Let's say I have another curve here, example 2. You have a curve like this coming up to here. I'm drawing this in blue color. Okay, call this curve part 1. Then you have another curve. You have a signal that's made of 3 different equations. Then you come here. Okay, this called this equation part 2. This is the second equation. Then you have another equation. Let me draw this as another color. Three. So section 3. You have 3 sections here. Will you be able to apply Simpson's rule here? Let's see whether we can. What we can do is we can write the Simpson's equation for each segment of the equation. For each segment, there's a blue segment, there's a red segment, and then there's a purple segment. First, look at the blue segment. If you look at the blue segment, okay, let's say it's starting from 0. Okay, let me put the marks here. 0, 1, say 0 to 3. Let's say maybe this, they're not in scale. Okay, in the middle somewhere here, call this call this 2 or something. Say 1.5, maybe. 1.5. Okay, then we have another segment that starts at 3, which is called the red segment, and ends at 5. Another segment starts at 3 and ends at 5. Is anybody having some problem, technical problem? I can hear some noise. So there's another, starts at 5. Let's say this is starts at 5 and then this is 6. So segment, the blue segment goes from 0 to 3. The red segment goes from 3 to 5. And the purple segment goes from 5 to 6. Let's assume there are 3 different equations. Therefore, we have to do them separately. Let's look at the blue segment. The blue segment goes from 0 to 3, right? Naturally, you want to split that into 2. Definitely, you will split that into 1/2, right? The midpoint will be 1.5. Then if you know the midpoint, what is the midpoint? Then you can find the corresponding, you know the equation, then you can find the corresponding value. Let's say call this 1.25. 1.25. Call this 1.25. And at 3, okay, this is the place where both red and blue touching each other. Let's say at the midpoint, at 3, the corresponding value is 5. Okay, so you're done breaking up into 2 segments for the blue segment. Any question on this?
No, sir.
Okay, now you do the same thing for the red section. You want to split that into 2. And then red is going from 3 to 5, right? So what is the mid value from 3 to 5? 5 minus 3 is how much? 2, right?
Yes, sir.
Yes, sir.
2 divided by 1. 2 divided by 2. 2 divided by 2.
1.
1, right? So 3 plus 1.
4, sir.
4.
Therefore, you're going to, that's the exact midpoint, 4. That means the length from year to year, we don't want to, you know, right, the length from year to year, 1. Right. You will do that for all. $1.5. Okay. So you have to now, once you split them up, then you have to find the corresponding value. For 4, what is the corresponding Y value? The corresponding Y value, let's say you know, is 3.25. Okay. So at 5, again, you project an horizontal line. And then let's say you know the value It's around 2.5. Okay, at this point. Okay, are you guys all right? Okay, let's do that for the purple region, the purple section. Purple section from 5 to 6 starts at 5 and then end at 6. So what is the midpoint? From 5 to 6, you want to split into 2, right? So what is the midpoint? What is the midpoint? Yeah.
5.5, sir.
Okay, 5.5. Okay. Because from year to year is 0.5. From year to year is 0.5. So midpoint is then the corresponding value for this. Corresponding value is 2. Okay, these are values assuming that you know. Assuming that if you know the what is the equation here, then you'll be able to find. If you plug in 0.5 here, then you know what is the y value. The reason why we know the equation, but some of the equation may be very difficult to integrate. That's why we are doing this numerical. So what we need to do, we have to do, now we do have to apply the Simpson's formula. We start at 1, the blue section. Okay, do you remember the formula is h over 3 y left plus 4yc plus yr. So h, what's the h here? Is 1.5 or 3. And what is yl? Yl, look at the yl. So this is the, for the blue section, this is the yl, right? YL is 0, right or not? YL is 0, the value is 0 plus 4. Then what is YC? This is YC. Which is 1.25. I made a mistake in my notes. The Google is not supposed to be f1.25 because I put not this. We're going to get directly the value from here. The value from here is height, which is 1.25 is given to you. And then plus what? YR, 5, right? So if you do the math, you will get 5. Is it okay? Can you guys follow this part?
Yes, sir.
Okay.
Okay, then you do the same thing for the next one. For now, we go to the red part, red. The red part applying the same formula. The red part, the interval, the h is 1. Still the same formula, h is 1. So it's going to be 1 over 3. What is YL? Left side, left is 5, right? Five plus 4. What is the midpoint? In the red region, 4. No, it says, sorry, not 4. It's 3.25 right here. YR, the right side, is this one, the value corresponding to this. What is that?
2.5, sir.
Huh? How much?
2.5.
Okay, that 2.5. Good job, G. Which is equals to 41/6, which is approximately 6.83. It's approximately 6.83. Then we repeat the same thing. Repeat the same thing for the third part. The third segment, if you note carefully, the height this is age, which is 0.5. So 0.5 over 3 . Okay, if you look, the segments start at this point, and when the left hand point is 5, the corresponding value is how much? 2. Sorry, not 2. The corresponding value is also 2.5. Four times the midpoint at 5.5, you are getting 2. And then finally at 6, 0. We work that out. It's going to give you 163 divided by, 7/4, which is approximately 1.75. 1.75. To sum up everything, since it's going from 0 to 6, fx dx is equals to, okay, you just add them up. 5 plus 6.83 plus 1.75. 5 plus 6.83 plus 1.75. How much is it? How much?
13.53.
13.58, sir.
Okay, 13 point how much?
13, sir. 13. 5.8.
5.8.
5.8, sir.
5.8.
So that's the answer.
Yes, sir. Exact answer.
Okay, I already covered one concept today, so I want to give the students some time to